This tracker is running a Kalman filter, the same algorithm used in radars, missiles, and self-driving cars for 60 years. It's tracking perfectly. Then the target turns. Seconds later, the filter has thrown away every real measurement and is confidently tracking nothing. It didn't fail because of noise or a bug or bad tuning. It failed because of an assumption buried in its math. And once you see it, you'll understand why an entire family of algorithms had to be invented to fix it. A Kalman filter is a prediction machine. Every cycle it does two things: predict where the target will be, then correct that prediction with a measurement. The magic is in how it weighs the two. It trusts its prediction more when measurements are noisy and trusts measurements more when its prediction is uncertain. But predicting requires a model of how the target moves. This filter uses the most common one, constant velocity. The target keeps doing what it's doing, and here's the part everyone glosses over. The filter doesn't just use this model, it computes its confidence from it. Watch the dashed ellipse around the estimate. That's the validation gate. The region where the filter believes the next measurement must fall 99% of the time. Measurements outside the gate get rejected as clutter, birds, noise, some other object. That rejection is a feature. Real sensors are full of garbage returns, and the gate is how trackers survive them. On the straight leg, this works beautifully. The gate is tight, every measurement falls inside, the estimate rides the truth. Textbook. Now the target begins a hard turn. About 5G. Nothing exotic for a fighter or an agile drone. Look at the bottom plot, that's the innovation. How far each measurement lands from where the filter predicted it, normalized by how surprised the filter is allowed to be. The turn starts and the innovation climbs immediately. The filter is being told every tenth of a second the target is not where your model says. Here's where the trap springs. The filter's uncertainty. That gate was computed assuming constant velocity is true. So the gate stays small because according to the model, nothing unusual can happen. The measurements drift toward the edge of the gate, and then out of it. And now the feature becomes the failure. The gate does exactly what it was designed to do. It rejects the measurements. The real target, turning away, looks statistically identical to clutter. The filter throws away the truth to protect itself from lies. With no measurements accepted, the filter runs on pure prediction. Dead reckoning along the old heading. The estimate and the target diverge. After enough consecutive rejections, the tracker declares the only thing it can: track lost. And notice what the innovation plot shows. The filter was maximally surprised the entire time. The information that the model was wrong was right there, in the filter's own internals. It just had no mechanism to act on it. So the obvious fix: make the gate bigger, crank up the process noise, tell the filter trust your model less, and that works, sort of. On the right, the same filter with high process noise. The turn doesn't break the track, but look what you paid for it. On the straight legs, the estimate is noisier. The gate is huge. And in real clutter, a huge gate means you start accepting garbage. You've traded loses maneuvering targets for worse at everything always. This is the actual insight, and it's bigger than Kalman filters. A single model cannot be simultaneously tuned for two different behaviors. Quiet flight and hard maneuvers are different dynamics. Any single filter must compromise between them, and the compromise is bad at both. Which is why, in 1988, Blom and Barshalom formalized what modern trackers actually use: the interacting multiple model filter. IMM's move is almost embarrassingly direct. If one model can't cover both behaviors, run several. One filter assumes constant velocity. Another assumes a maneuver. All of them run in parallel every cycle. The clever part isn't running them. It's the mixing. IMM watches which model's predictions match the measurements and continuously reweights. Watch the bottom strip. On the straight leg, the constant velocity model earns the weight, and you get its tight, low-noise estimate. The turn starts, and the CV model's innovation explodes. The exact signal our first filter ignored. The weight flows to the maneuver model within a few cycles. The gate follows the model that's currently right. The innovation stops being a symptom you suffer and becomes the signal you steer by. That's the whole trick. So, trackers don't lose maneuvering targets because they're noisy or slow. They lose them because the filter's confidence is only as honest as its model, and a confident, wrong model rejects the truth by design. IMM fixes the model problem, but notice what we quietly assumed this entire video: that we know which measurement belongs to our target. Target, one blip. Put two targets near each other, or one target in real clutter, and a new question appears that no amount of filtering can answer. Which measurement is mine? That's data association. It's arguably the hardest problem in tracking, and it's where we're going next.